Good morning, students. Today is July 12th, Thursday, I believe, if I'm not mistaken, or Wednesday, I'm sorry. Today is Wednesday, July 12th. We're going to do our session. We're going to work on 6.2. But the more important thing is on Monday, you have your exam 3, okay? The syllabus is here. We will cover 6.2. I'm not going to record a session. I'm going to give you that day to review your work and study. I will not record a class tomorrow. You will get the day off, but do study. Now, if you ask me to do something, email me. I'll be happy to record and upload it. So I will go over 6.2. By the end of today, you should be able to do 6.2. 6.2 is a little hard, I'll have to admit it. So I'll try to do it slowly. If you need help, just ask, send me the messages like some of you do. I'll be happy to record a solution for you, okay? So let's get right into it. Okay, guys. So bear with me a little bit, hopefully. All right, we're going to talk about discrete random variables. So it's going to be a strange case, okay? We're going to talk about binomial experiment, okay? In a binomial experiment, you either have uh, uh, success or failure. So I'll give you a simple example. Say you decided to roll a die 6 times, and you want to know if you're going to get a 6, 0 times. What's the probability that you're going to get a 6 0 times? You're going to get a 6 1 times, 1 time, 2 times, 3 times, 4 times, 5 times, 6 times. You want to know that. That's an example of a binomial experiment. What are some of the qualities of a binomial experiment? The experiment is performed a fixed numbers of time. In our case, it's 6, and each experiment is a trial. You're tossing a coin or rolling a die. That's the trial. The trials are independent. Your first 6 doesn't have any effect on your second 6 or third 6 or no 6. This means the outcomes of one trial will not affect the outcome of the other trials. For each trial, there are two mutually exclusive disjoint outcomes. So each time you roll you toss you roll a die, you could either get a 6 or not a 6. What's the probability of getting a 6? 1/6. That's called probability of success. What's the probability of failure? The probability of failure is 5/6 because 5 out of 6 times, you're not going to get a 6. So let's summarize it. You can read the slide yourself, but it's from your book. A binomial experiment is something like this. You decide that you're going to roll a die 10 times, okay? And you want to record how many times you get 6. What you want to know, you want to find out how many times, what's the probability of getting a 6 0 times, 1 time, 2 times, 3 times, all the way up to 10 times. Now, each time you roll a die, the the outcome, the probability that you're going to get a 6 is fixed, 1/6, and the probability that you're not going to get a 6 is also fixed, and it's 5/6, right? So it's a lot going on, but when we do a couple of problems, things will make a little more sense. So bear with me a little bit on this, okay? A little bit of fancy words. There are n independent trials in the experiment. Now, in our case, it was rolling the die 10 times. Okay. Let P denote the probability of success. In our case, the probability of success was 1/6 because the probability of getting a 6 was 1/6. And the probability of failure was 1 minus P. So let's do this here. Probability of success, 1/6. Probability of failure is 1 minus 1/6, which turned out to be 5/6. Okay, let X denotes the number of successes for n independent trials, then X has to be between 0 and n. That makes sense. You're rolling a die 10 times. The fewest number of times you could get a 6 is 0, and the largest number of times you could get a 6 is 10. That's what this is about. We're gonna do some problems. I hope it'll make more sense. Okay, we're gonna patiently do some problems. Let me introduce you. Let's go ahead and do this. Okay, Now, I'm going to just take the question and do it, and I hope I have a solution here. Okay, let's try this one. Okay. So according to the American Red Cross, 7% of the people in the United States have a blood type zero negative. A simple random sample of four is obtained. What's X is X, the number of people X with blood type zero is recorded. Construct a probability distribution of the random variable. So basically what they're telling us, the probability that somebody will get zero negative blood type is 7% or 0.07. And if you're going to get four people, they could all be zero negative, only three, only two, only one. No. So that's what they're talking about. So they want us to do a tree diagram. And in this case, since you would either have somebody with a probability of zero negative blood type or not, so we are going to just call it probability of failure and success. Now I'm going to take this, put it here. I don't know how well you can see. I can make it a little bigger, but not too big. So the first outcome could be a success or a failure. The second outcome could be a success or a failure, success or a failure. So it kind of branches out like a tree and it gets quickly unmanageable. And you will see there are actually 1, 2, 3, 4, 5, 6, 7, 8, 16 outcomes. Okay. It really is going to be 2 to the power 4, 2 to the power 4, which is 16 outcomes. And 16 is a lot. You're doing four sample, and there's 16 different outcomes. So here, what's the probability? All out of four. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 16, my bad. Okay. So four successes, three successes, three successes, two successes, three successes here. Okay. Success, failure, success, success, so on and so forth. So the question, we are going to use this to find the question. Here, zero successes, right? So out of 16, what's the probability? All four will have zero negative. The answer is 1 out of 16, isn't it? So let me get the problem from your book and we'll answer some of those questions. Okay, well, so we did the tree diagram, right? Compute the probabilities for each value of the random variable x. The random variable x has values 0, 1, 2, 3, 4. So let's do it. Okay, the probability of none of those people, none of those people will have zero negative. Okay, there's only one way, F, 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 fail, 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 fail. So that's going to be 1/6, 1 over 16. There are 16 different outcomes according to the tree diagram. One is that. Now I'm going to quickly go ahead and do probability of all four being all four being zero negative. That's also 1/16 because there's only one case. This one goes here, this one goes here. The rest are a little tricky. Okay, so let's do this now. Let's do this. I'm going to put this here. I don't need this. Well, let's put it here. Let's put it here. Let's put this here. Probability of 1. Now, you could get one success here, 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 and here. All together, let me see if I missed anything. Exactly one success. So that's going to be 4/16. I'm going to leave it at 4/16, but of course you can write 1/4. What about 2? What about 2? Well, let's hide this. 2 will be this. 2 successes. 2. 1, 2, 3, 4, 5, 6. I'm getting 6 out of 16. Then I have one more. 0, 1, 2, 3. I have the third one. 3 successes. Two of them here. I'm just going to leave it like this, okay? I'll go back and check in a second, okay? I'm getting 4, if I'm not mistaken. That sounds about right to me. 4. Okay, so 6 plus 4 plus 4 plus 1 plus 1 is 16. That's a good sign. I've accounted for everything. So that's how you find the probabilities of a binomial distribution by drawing a table, drawing a tree diagram or a table, whatever you want to call it. Now, the catch is the tree diagram gets really hideous after a while. Okay, so we're not going to always talk about tree diagrams, and that's the whole idea. How else can we do it? So we're going to move to the next slide, next topic from the same section. Okay, that's the plan. Okay, now we have to actually do a little more work, but I'm not going to worry about it too much. What they're doing here is this 0.7%. I'll do one of them for you. Okay, so we did the computer construct the probability distribution table. Now, to find the probability, we have to do a little more work, just a tad bit more. So let me see. Let's do this one. Now, for this one, let's do this one. I'm going to get rid of this. Okay. Now that you know, what's the probability that all 4, that's going to have 4 slots. Okay. That's going to have 4 slots. I'm going to explain what I mean by slots. Okay. What's the probability that you choose the first one and that person is, I'm going to write first, second, and third, and fourth. Okay. So the first person, there's only 7% chance. Okay. 7%, according to your book, is 0.07. 0.07% chance that the first person, that a person will be zero negative. So what's the probability? SSS, you got a bunch of successes, so it's going to be 0.07, and the second person is going to be 0.07. They're all independent. The good news is you can simply multiply 0.07, and this is 0.07. Okay. Now, what's the probability that the first person is zero negative, the second is also zero negative, third is also zero negative, fourth it's also zero negative. You multiply the probabilities because they are independent. That's one of the conditions. So instead of writing 0.7 times 0.7, I'm just going to say 0.07 raised to the power 4. And it's going to be a tiny number. Okay. And I'm going to be fine. I'm going to just leave it like that. Okay. That's the probability. So we'll do 1. What's the probability of all 4? Now, if we are going to be very patient, let's take the one with all of them, none of them are zero negative. Okay. How do we do that, guys? How do we do that? So this is going to be, remember, if 7% of the people are zero negative, 93% of the people are not zero negative, and 93% means 0.93. Now, this is the only situation where that'll happen, right? Failure, failure, failure. You multiply all of them, and it's going to be, I'm going to go back here in my calculator, and this time I'm going to say 0.93, 0.934, and I'm getting this. I'm going to check some of the answers in the book, okay? 0.741, 0.74. Let's see if we messed that up. 0.74, we got that one right, okay? They're all fair. Now, this one is interesting, guys. Now, instead of doing it, I'm going to just walk you through if you don't mind. So, guys, what's the probability that that you will have one success? Now, one success can happen in your first trial, all failure. In your second trial, they're all failures. In the third trial, the rest are failures. In the fourth trial, the rest are failures. So you're going to find the probability of this. These are all addition rule. These are disjoint events. So you're going to find the probability of this, probability of this, probability of this, probability of this, and you're going to add it up. Now, the probability of a success is 0.07. There's 1.07, and there are three failures. That's why you have 0.93, the probability of failure raised to the power 3. Exact same thing, 0.07 to the power 1, 0.93 to the power 3. Same thing goes on here. And if you add it up, you get 0.22522. Now, the good news is we won't do it using the tree diagram, but the tree diagram is the basic building block of what we're going to say. And you can do this one, 0, 1, 2, 3, and then they're really the same. Really the same. It's a little tedious, but I'll do something from your book and explain it to you in a slightly different way. And that's how you're going to generally do it. Let me see what's going on. All right. All right. So guys, instead of, okay, this is the formula I'm looking for. So this is what we're going to stick to. And I'm going to go to your book and do a problem from your book using this concept. Okay, it'll make a lot more sense. So what we're doing here, so we don't have to do the tree diagram. Think of it this way. Think of it this way, guys. You have n trials, there are n slots. Think of n boxes. Each box can be either a success or failure, right? And you know the probability of success, you know the probability of failure. So you want to know how many ways you can get three. Let's say you have, let me grab a problem from your book, okay? Grab a problem from your MATLAB that I assigned. And I'll explain that formula using an example from your book. It's That's probably the safest thing to do. All right, I have the answers here. I'm going to come and check the answers with you guys, okay? Okay, so what we're doing is a typical problem from your book, and we're going to show you why that formula, the one we just discussed, will make sense, or how to use that formula above this. All right, let's bring this guy here and be a little patient. It's a little messy. All right, so this is here, and this is my real problem. And let this be here. According to a study done by Nick Wilson of Otago University, Wellington, the probability a randomly selected individual will not cover his or her mouth when sneezing is this. So that's the probability of success. You know, it sounds weird, not covering is success, but it is. I'm going to say probability of success. Generally, we call it P. Okay, we say P. P is given. It's called probability of success is 0.267. And 1 minus P is the probability of failure, and that's also given, which is basically if the probability of success is 0.26, probability of failure will be 1 minus that, always 1 minus that. Why? Because it's either success or failure because they're mutually exclusive, 0.733. I'm going to call it 1 minus P. Now you have to understand 1 minus P is the probability of failure and P is the probability of success. Suppose you sit on a bench in a mall and observe people have it. This is complete part A through C. Let's see what part A is. Okay. This is probably a success, probably a failure. Part A. Part A says, what is the probability that 16? That's a large number, but that's okay. We'll survive. Okay. We can do tree diagram. It's going to take forever. All right. All right. So what it says is the probability that among 16 randomly selected individuals, okay, you're in the mall and you're watching people, exactly 8 of them do not cover. Okay. 8 of them do not cover. So you have 16 people. Okay. You have 16 people. You have 16 slots. And I'm going to do the slot like this. It takes a little bit of time. Okay. I'm taking 16 slots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. I hope I have 16, but that's not a problem. I'll have to adjust it. Now I'm going to shrink them a little bit because I need the room. Now bear with me a little bit here, guys. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. Now, guys, so the first slot refers to the first person, second slot, second person. Okay, so I want to know, the question wants me to find out, if you read the question again, it says out of 16, 8 do not cover. Okay, will not cover, do not cover. So the probability of success. So 8 of them will not cover. So out of 16, now we don't know which 8. Are they the first one through 8? They could be anywhere. So for that, you have to choose 8 boxes out of 16 using combination because they could be anywhere. Okay. 8 out of 16. So you have to very carefully say, okay, um, I'm going to write it like this. C 16, 8. You're going to choose 8 boxes, and that can be done in this many ways. 16, choose 8. Once you choose which 8 boxes where people don't cover, the rest people will cover, right? So here, this will be this probability, the 8 that cover is going to be 0.2, sorry, 8 that don't cover raised to the power 8, and the remaining 8 will cover, and the probability that they will cover is 0.733, which is good. More people tend to cover. And that raised to the power 8. Why? Because all these are independent variables, okay? 8 of the people you choose, they could be anywhere, the first 8 or the second, not the first one, but then 8 of them, then there could be anything. So to account for all different cases, and you don't want to add them, it'll take you forever, like we did with our little blood negative problem. This is what this is trying to say right here. Right here. It's a little hard. I'm going to do a few more. Hopefully things will make sense. So what I'm going to first now do, I'm going to do my problem. I'll solve it, check my answer. So let's see. 267 raised to the power 8. Now, then the next one is times 1 minus 0.267. That was our 733 raised to the power 8. I'm getting this number, and it's time to check our answers. Okay, let me check our answers first, okay? Just to make sure I didn't mess up. 0.0277, that's fine. That's not bad. All right, so guys, let's try the next one. What's the probability that 16 are chosen and fewer than 6? Oh boy, that's going to be a lot of work. Be a little patient with me, okay? Fewer than 6 do not cover. Okay, let's take this. I'll do it very patiently. Did A. Okay. Fewer than 6 don't cover. What does that mean? That means, so you chose your 16 people, same as before. So the number of people that do not cover is your success. So it could be one that don't cover, probability that two of them don't cover, probability that three of them don't cover, the probability that four of them don't cover, the probability that five of them don't cover, all those things. What's the probability that among randomly chosen fewer than 6 do not cover? You fewer than 6, they're meaning strictly fewer than 6. So one don't cover, two, three, four, five. Okay. So let's find, and you have to do the 0 too. Don't forget the zero case. So what I'm going to do, this is my probability of success. This is my probability of failure. So I'm going to first say out of 16, nobody covers. Okay, let me double check. Suppose that okay, let me go back and read the question again. What's the probability that among the 16, fewer than 6 do not cover? Fewer than 6 do not cover their mouth. I have to find that none of them cover their mouth. That's fewer than 6, 0. So I will take this, 16 choose 0, okay? And this will be 0, and this will be 16. Okay? And I'll tell you, this answer is not going to be valid anymore. This really plays trick with your brain, this problem. So what I have to do is, let me bring this question here. Fewer than 6. to just do it very carefully. Let's put this guy here. So those properties are here. I don't need that text. Okay. So fewer than 6 do not cover. So exactly 5 don't cover. Exactly 4 don't cover. Exactly 3 don't cover. Exactly 2, exactly 1 doesn't cover, and none of them covers. So this is the first one. Then I'm going to do this one. This one is going to be only 1. And this one is going to be 1. And this one is going to be 16 minus 1, 15. Why, guys? If 1 doesn't cover, 15 covers. None of them covers, all of them, none of them. This is 0. The powers should add up to 16, okay? Just like here. If this is x, this is n minus x, okay? So, and I have to do it for 0, 1, 2, 3, 4, 5, okay? So I will do it here. I will do it here, but I will, actually, I'm better off doing it on the calculator. Let me try it here, guys. And I have to do it very carefully, okay? So this, I'm going to take this same thing, excuse me. I'm going to do 0. All right. I'm going to put a 0 here. I'm going to put a 16 here. Okay. And let me bring this, copy this here, clear everything. So this is the, I hope you can see, this is the one that 0 success. Okay. And then I'm going to do 1 success. 1. This will be 1. And this will be 15. And then I'll do 2 successes. This will be 2. 16 choose 2. 2. And 16 minus 2 is 14. Then I will do 3 successes. 3 is to the power 3, and 16 minus 3 is 13. Do you see the pattern? Then I will do 4 successes. 4, 4, 16 minus 4 is 12. Then I will do 5 successes. And I'll stop here. 11. And I have to add them all up. They're mutually exclusive. So I'm going to take this first one, put it here, plus take the second one, put it here, plus take the third one, put it here. So 0, 1, 2, 3, 4, 5. I have 6 of them, right? All right. So I did the first one, second one, third one, then I have 3 on top. So easy to mess up. And I have one more, the third one from Dawn. Look at 0.76300. Let me go back and check my answer. Not bad. I got it. So guys, this is B, right? Yeah, B, I got it. Now, guys, it's a little hard. I'm gonna try to explain it to you again. Okay. I have I have 16 situations. Okay. From that, I am gonna find out 5 situations, 4 situations, 3, 4, 5 is less than 6, 4, 3, 2, 1, and 0. How do I do it? Using this formula. Okay. For the first one, n is in our problem, n is 16. Okay. Uh, probability of zero, probability of no success. This is where it goes. Okay. 16, choose zero. And then this probability of success to the power zero. If this is zero, this is zero, and minus zero is 16. So when x is one, this becomes 16, choose one. That's where you have, that's what you have. This power to the power one, this x, and the power is n is 16 minus x, which is x is 1, so 16 minus 1 is 15. So take advantage of the calculator and remember this formula. It's a little hard, and it's there. We did it. I'll be happy to do one or two more. You just have to ask me. Okay. So what we're going to do is we're going to go over the next tiny little thing from your book, and to find, okay, when you have a binomial distribution, guys, when you have a binomial distribution, you find the property the way we did, and I'll be happy to do one or two more if you guys need my help. You can find the mean mu x by n by p. N is the number of trial, p is the probability of success, and standard deviation by using this formula NP. N is the number of trials. In our case, it was 16 in our previous example, and probability of success in our previous example was whatever it was, right? Let's see if I still have it. This was the probability of success, 0.67, 0.267, and 1 minus p is going to be 1 minus 0.267. So you can find this. Now, these formulas are a little hard to prove why they are the way they are. I will upload a video on how to prove these formulas today. Actually, it's from YouTube. Another professor did it. It's a nice proof. I will put it there for you to look. You don't have to look at it. It's an open book exam. You can write it down. These are the formulas we use to find the probability, the mean and the standard deviation of binomial distribution. I'm more interested in finding the probability using this formula. I'm more interested in this. Most of the questions are about this, just to let you know. I know it's a little harsh for you guys. Again, I was fit to do something. I'll be happy to upload some videos for you guys. Other than that, I'll call today and do some problems, and let me know how you do. All right. Thank you. No class today again. No class tomorrow. I won't record anything. You'll study. I will give you, let's go over the study guide a little bit. Okay. Here's the study guide. For exam 3, it's on July 17th on Monday. These are the sections that I will cover. It will be cumulative, 20-25 questions, not much more. And take the exam on time. I won't be able to give you extension. I gave you extension for July 4th. People had vacations. So I was trying to be nice. I won't be able to give you extension on this one. Keep that straight. Okay, guys, thank you.